Okay, let's start again. So before we move on so today we're going to discuss fermions and possibly gauge fields, so that we will have all the ingredients actually to look at gauge theories like QCD or other theories. Before we do that, I just want to go back to a question yesterday about the dependence of the beta function on A, okay? And I'll tell you the answer to the question. I'll tell you why somehow I wanted to think about it. So remember, the way we define the beta function is from the dependence of the couplings on our cutoff scale A. Okay, so this defines minus beta alpha salute, like that, okay? So you can really think, as we said yesterday, we can really think of this as a flow in a space of parameters, okay? And in this respect, A is nothing but the time of the flow, if you like, okay? So this is a parametric curve, which is parameterized by A, okay? So in the space of couplings, so, you know, whatever, G1, G2, this equation defines a curve, and A is just the time with which you flow along this curve, okay? And the beta function is just it just defines the tangent to this curve at any given point, okay? So clearly, if the relation between A and G is invertible, you can always trade an A dependence and rewrite it in terms of the G couplings, okay? Now, the thing that is a little bit maybe tricky here is that, you know, the definition of the couplings, of the bare couplings that we have in the action, in a sense, is a choice. You can always reparameterize your flow, okay? So you can always define a new set of couplings, G prime, that are functions of your original couplings G, okay? Now, if this relation is sufficiently sort of smooth and invertible, you can show that the beta function transforms covariantly. Actually, this is a nice exercise. Okay, you can show that the beta function for these primed couplings, so beta prime alpha of G prime, is just d G prime alpha dg beta times beta of G, okay? Where clearly this beta is not the same as the beta function, it's just an index, okay? So you can always think of schemes where things may go wrong, okay? Where this transformation is singular enough and things may go wrong, but I would say that these are just pathological schemes and one should try to avoid them, okay? The nice feature, the nice consequence of this relation, by the way, is that if you have a fixed point in a given scheme, okay, remember we defined the fixed points by saying that beta alpha at G star is equal to 0, then because of this relation, beta prime at G prime star is also equal to 0. Okay, so the existence of the fixed points that we were mentioning yesterday is scheme independent. Okay? And actually, if you take a derivative of this equation with respect to the couplings, once again, you can show that the eigenvalues, these lambdas that we discussed yesterday, are also scheme independent, okay? Which is important because remember we said the number of relevant parameters is the number of parameters that you need to tune in order to get a given physics in the low energy regime, okay? And that is completely independent of the choice of scheme, okay? So that's that. Now I can go back to fermions. Well, actually, we can start fermions. So, fermionic fields, we will be, again, in Euclidean space. And in this case, because I don't want to get into the complication of defining fermionic representation in arbitrary dimension, I'm going to stick to d equal 4. Okay? So d is equal to 4, and we are in Euclidean space. Okay. So in the continuum, we can write an action. Let's consider free fields to start with, which looks like that, d slash plus n psi of x, where d slash is the usual d slash, so it's the contraction of d mu with the gamma matrices, and these gamma mu are Euclidean gamma matrices, which we can write in the following form, where E4 is the identity and EK are the Pauli matrices. Okay, so these are 2 by 2 blocks, and with this convention for the gamma matrices, we've got that the gamma matrices are Hermitian, all of them. Okay, the anti-commutator gives you a sort of Euclidean Clifford algebra structure, so gamma mu is 2 times delta mu nu. We can define a gamma 5 matrix, which is just the product over mu of gamma mu's, and then gamma 5 is also Hermitian, and gamma 5 squared is equal to 1. Okay? So this is in a nutshell the free fermionic field in a continuum theory in 4 dimensions. Okay? So again, remember when we studied the particle content of the free theory for the scalar case, we looked at the spectral decomposition of the 2-point functions, of the 2-point function. So without, again, getting into the details, I mean, just write down the spectral decomposition for a fermionic 2-point function. So if we compute a correlator psi of x, psi bar of 0, in Euclidean space, this looks, so there is a contribution to this correlator from every physical state, okay, and the spectral decomposition looks exactly like the one we discussed for the case of the scalars. So you get the sum over all the states, so all possible momenta, all other quantum numbers. We have a relativistic normalization, and then we get a decaying exponential in Euclidean time. We get the usual oscillating term for the spatial momenta, and then the only difference is that, you know, these, remember, are spinors, so they carry spinorial indices, if you like. Okay, so this is a matrix. In 4 dimension, it's a 4 by 4 matrix, and here there is a matrix structure which looks like this, alpha AB, and then there is a spectral weight, which I'm going to call Z alpha squared. Okay, so this is the equivalent of the matrix element between the field and the physical state, modulo squared. Okay, so keep this in mind, because in a moment we are going to analyze the particle content of the naive discretization of the fermionic action, and so we're going to do exactly the same calculation that we did for the scalar case, and we will want to compare to the expected spectral decomposition. Okay, so this is so again here we will discretize using the sort of naive prescription that I used for the scalars. So we're going to replace the integral with a sum over all the lattice sides, and we're going to replace the derivative with a finite difference. So my lattice action, now remember the fields, they're matter fields, they're defined on the lattice sides. So this is the sum over x, psi of x. And then I will discretize the derivative as 1/2 of the sum of the forward and the backward derivative, and then gamma mu psi of x plus m psi bar psi. Okay? So that's the prescription we used for the scalars. You replace integrals with sums, you take finite differences, and you declare that this is your lattice action. So then again, we will do exactly the same exercise. We're going to look for the propagator. So the thing that we want to focus on is the particle content of this theory, okay, in the free case. So we're going to do exactly what we did for the scalar. We're going to compute the propagator, and then having the propagator, we're going to compare the two-point function with the spectral decomposition, and we're going to derive the particle content. Okay? So in order to compute the propagator, we go to momentum space again, and we're not going to do the detailed calculation. It's exactly the same kind of calculation that we did for the scalar case. So we can write directly the free the kinetic term here in momentum space as, again, a delta of P minus Q, and then something that we can write like this, P tilde mu gamma mu with a factor of I plus M. Okay? So remember, this is going to have spinor indices A and B. This has got spinor indices A and B. In this case, the spinor indices refer to the gamma matrix, and you should think of this as being the identity in spinor space. Okay? So that's my propagator. Let me tell you what P tilde is. So P tilde is 1 over A times the sine of A P mu. Okay, and here you see that this is different from what we got in the scalar case. Okay, in the scalar case, the action is quadratic in the derivatives. Okay, and we got there sine squared of AP divided by 2. In this case, the linear in the derivatives. So actually, this calculation is, in a sense, it's even simpler, and you just get the sine of A mu. Okay? And again, if you expand this in the limit where AP is small, so if you look at the theory close to the continuum limit, you recover what you expect. Okay? So P mu times 1 plus corrections that are A squared, P squared. I mean, this is nothing but a statement that you discretize the derivative correctly. So this looks like a small change compared to what we saw for the scalar case, but it actually has quite deep sort of consequences. So in order to see that, we're going to compute the two-point function, and we're going to see what we get. Okay, so we did the computation for the scalar case in full detail. And so we're not going to do this computation here in detail. I'm just going to give you sort of the main steps, and hopefully after Monday this will sound familiar. Okay? So remember, the idea is that we want to compute psi 0. Okay? And we want to compute this as the inverse Fourier transform of the kernel in momentum space. Okay, so the propagator momentum space, which is the inverse of the kernel. Now, if you remember the computation that we did for the scalar, what we did is that we isolated the integration over P4, okay? And then we looked at the poles of the propagator in the complex, or in the complex P4 plane. And the poles of the propagator gave us the exponential decay of the two-point function. Okay? So we're going to do exactly the same. We're going to look at the poles of the Fermion propagator, okay? Which is the inverse of K naught. So in the denominator, of delta 0, we have a P tilde 4 squared plus the sum over K of P tilde K squared plus M squared. Okay, this is the denominator of the propagator, which again we can rewrite as 1 over A squared, factoring out the dimensions. Okay, then we have a sine squared of AP4, and then the rest I'm going to call MP tilde squared. Okay, where MP tilde squared is just this. Is the sum over K of the sine squared of APK plus A squared M squared. Okay, so these are all dimensionless quantities. Everybody happy so far? Okay. Then the next step here is that remember we introduced a complex variable z, which is e to the I AP4. Okay, and then the integral over P4 reduces to the integral over the unit circle. Okay, and so the game is to re-express this denominator as a function of z and find the poles that are inside the unit circle in the z plane. Okay, so if we do that, we can write the sine of AP4 as minus 1 over 4 times z squared plus z to the minus 2. Okay. And then this expression here, so the denominator can be rewritten as, sorry, this is the sine squared, obviously. And then the denominator can be rewritten in the following form. And again, there is a little bit of algebra in between, but you can do that offline. I don't think there is any advantage in watching me doing trigonometric functions. So the sine square of AP4 plus M tilde P squared we can rewrite as minus 1 over 4 z squared. Please check times z to the power 4 minus 2fz squared plus 1. Okay, where f is just 1 plus 2 mp tilde squared, which is a number which is greater than 1, given that m squared is always positive. So the first thing to notice here is that so the denominator of the free Fermion propagator is a quadratic function of z squared, okay? Which means that we can solve the quadratic equation, and we're going to get two solutions, a z squared plus and a z squared minus, okay? And this is f plus or minus the square root of f squared minus 1, like that, okay? And so you see immediately that the modulo of z plus is greater than 1, okay? And the modulus of z minus is smaller than 1. And so for each value of z squared, you've got two values of z, okay? And so we have two solutions that are outside the unit circle, and we have two solutions that are inside the unit circle. Okay? So we have two poles inside the unit circle. And they correspond to plus and minus z minus. Okay, so in the z plane, we've got minus z minus plus z minus z plus minus z plus. Okay, so when we do the integral around the unit circle, this time we pick up two contributions. And this is just a consequence of having swapped the sine squared of AP over 2 with a simple sine of AP4. Okay? So we can write, I'm going to get rid of this, just keep it in mind, because when we get to the final answer, we will want to compare to this, okay? So let's get rid of that. We get two contributions from the two poles that are inside the circle. And so we can write the two-point function in the following form. Remember, we've done the integral over dp4. Okay, so we still have the integral over the spatial components. And then we have the factor that came from the oscillating phase, which will look like this. And then we have the residue at the pole, which looks like that, omega PA times, and now we get two contributions, which I'm going to write explicitly, so bear with me for a second, and then we discuss the content. So we have a sinh of omega PA minus I, the sum over K, gamma K. We have a sine of pKa plus AM plus. So this is the contribution from the first pole. And then we have a contribution from the second pole, which goes like minus x4 over A. And then we get the minus gamma 4, the same factor, PA minus I times the sum of K, gamma K sine PKA plus AM. Plus AM, like this, close the parenthesis, and I need to tell you what omega p is. Okay, so omega p is the value of P4 that corresponds to these poles. Okay, and so we get that e to the minus omega p A is just 1 plus m tilde square p minus m p, like that. Okay? So this is the value of P4 that corresponds to the positive solution, and so Z minus is going to be e to the minus omega p, okay? And the other solution corresponds to P4 going into P4 plus pi over A. Okay? And P4 is equal to I omega of P. Okay? So with a little bit of algebra again, you can turn this expression into the following. You can show that the sinh of A omega p is equal to m tilde p. Okay? And if you take the limit where all the quantities are small in units of A to the minus 1, you can show that omega p satisfies the usual relativistic dispersion relation plus correction. Okay? So this was a little bit quicker than on Monday, but it's exactly the same. It's exactly the same sort of derivation. Okay, so you look for the pole, you use the residue theorem, you get the expression for the 2-point function, and the exponential decay is dictated by the location of the poles. Okay, now you see here the fact that we have two solutions, okay, is directly related to the fact that that everything, that P mu tilde is 1 over A sine A P mu. Okay? So if you shift any P by pi over A, you get the sign of AP plus pi. Okay? This is minus the sign of AP, and because in the equation that gives you the poles everything is quadratic, you automatically get another solution. Okay? So the fact that we have a first order equation, I mean the fact that the Dirac equation is first order in the derivatives gives you here a factor of AP in the discretized momentum, and this means that when you're looking for poles, P4 and P4 plus pi over A give you exactly the same answer. Okay? So there are two solutions where before you had only one. So you already see that the particle content here is not going to be the one that you expect naively, right? This is what you would expect naively. A decaying exponential with just one contribution that goes like P slash plus M. Okay, if we look at the dispersion relation, okay, if we look at omega P as a function of P squared, you see that for the case of the fermions, this is minus pi, let's write it like this, function of AP, plus pi. Let's set the spatial momentum to be, just in one direction, okay? So that I can plot it simply like that. Omega looks like that, like this. Okay. When AP is small, you are close to the origin, okay, and you get the usual sort of relativistic dispersion relation. Okay. If you look at the same function for the scalar case, look like that. Okay. Because of the sign of AP divided by 2, okay, the energy function for the scalar case doesn't go back to 0 when the momentum goes to pi in units of A. Okay? So you see, not only we have two poles, but we also have more minima of the energy function. So there are actually two, for each p direction, there are two regions in the Brillouin zone where you have a relativistic dispersion relation that looks like the usual dispersion relation that you would get in the continuum. So there are actually, you see, 2 points, if you like, inside the Brillouin zone where this particle looks like a relativistic particle, and it's here and here. Okay. So we can make this a little bit more quantitative, okay, in the sense that we can take this full expression and we can focus on the contribution that you get to this integral from the regions that are close to this minima. Okay? So how many of these minima do we have? We've got 8 of them. Okay? So we've got 2 to the power 3 minima. Okay? And they can be identified by vectors of integers nk, where nk alpha is equal to either 0 or 1, and k is equal to 1, 2, and 3. Okay? So there are 8 of these spatial momenta where omega has a minimum. We can write them. We can write a few of them explicitly. So we have 0, 0, 0. Let's write it like that. Okay. Then we're going to have P2 is going to be 0, 0, 1. P3 is going to be 0, 1, 0, etc. Okay. There are obviously 8 of them, and for each of them, you have a minimum of omega. Okay? So we're going to compute the contribution of this minima to that integral by expanding the integral around the minima. Okay? So around each minimum, so these minima are different regions inside the Brillouin zone. We're integrating over the whole Brillouin zone. So around each minimum, we're going to expand pk as pk alpha, which is the position of the minimum, plus some residual momentum k. Now if we do that, okay, we get 8 contributions, okay, and for each of these 8 contributions, there are 2 terms. Okay? So in total, we're going to get 16 contributions. Yes? So I'm going to rewrite the 16 contribution in the following form. As a sum, for alpha it goes from 1 to 16, e to the I p alpha dot x, and then the integral over d3k over 2 pi cubed e to the I k dot x minus omega of p times x4. This is going to be divided by 2 times k4. And then I can rewrite this term here in a compact form like that, times gamma 4 that multiplies the cos of p4 alpha times a times k4 minus I times the sum over j of gamma j cos of p alpha j a times k j plus m. Where in doing this, as you can see here and here, I have introduced a p4 alpha component. Okay, and again, p4 alpha is going to be n4 alpha times pi over a again, and n4 can be 0 or 1. Okay, so the minima give us 8 three-dimensional vectors. Okay, and now to these 8 vectors, I've added a 4th component, which can take 2 possible values. So now I've got 16 4-dimensional vectors, and that allows me to write these 2 terms in a compact expression like that. Okay, and this oscillating factor of minus to the power x4 divided by a has gone into here, because here you get a factor which is e to the I p for alpha times x4. Okay? So try to do all the explicit sort of steps offline. I mean, there is nothing particularly complicated. You just expand these functions after the change of variables, and the really sort of tricky part is to figure out that these two terms can be recombined by introducing a fourth component to these p alpha vectors that I defined up here. Okay? So try to do the calculation. This is the result, and now let's have a look at the result. And remember, we want to compare this to ip plus m, okay, which appeared in the spectral decomposition of the two-point function that I wrote at the very beginning. Okay, so you see, we're almost there in the sense that there's a gamma 4, there's a k4, there's a gamma j, there's a kj, there is an m. So everything is there except for these factors here. Okay, except for these cosines of p alpha a. And now remember that p alpha times a is either 0 or pi, which means that these factors here are either 1 or minus 1. Okay? So this really looks almost like that. And actually, you can show that for every choice of alpha, so for every choice of these components of the p alphas, you can find a matrix S alpha such that S alpha gamma mu S alpha dagger is equal to gamma mu cos p for alpha a. Okay? So these gamma matrices multiplied by combinations of plus or minus ones, okay, they are nothing but the usual gammas in a rotated basis. A rotated basis in spinor space. Okay? And so we can write our final expression for the two-point function in the following form. We have a sum over alpha from 1 to 16. We've got this factor here, p alpha dot x, and then we have an integral in d3k over 2 pi cubed, 1 over 2 k4, and then s alpha e to the ipx minus omega p x4, and then s alpha ip slash plus m, sorry, k slash plus m s alpha dagger. So this is really a collection of 16 particles with rotated in spin space. Okay? But really the bottom line is that if you look at the two-point function psi bar, the two-point function corresponds to a theory where in the spectrum you've got 16 states. Okay? And they all have energy omega p, which is given by this equation up there. Okay? So they're all such that when you get to the continuum limit, they look like bona fide relativistic fermions. So we started by discretizing one field, and we ended up with 16 particles. Okay. So this goes under the name of doubling. Okay. So if you discretize naively the fermionic action, you end up with a theory which has not just the one field, the one particle you wanted in the first place, but 16 of them. Okay? Does that make sense? Modulo the algebra. I mean, you have to do. There is no way you can get this without sitting down and doing the algebra. But the idea should be clear. Okay, and it's all a consequence of the fact that the Dirac equation is a first order equation in the derivatives. Okay, so that you get this signs AP instead of sine AP over 2 when you discretize the momentum. And this is not an accident, okay? It's actually a very deep sort of property which has, and is actually a theorem which goes under the name of Nielsen-Ninomiya theorem. And the Nielsen-Ninomiya theorem tells you the following. Where is the y and where is the I? Y, I first. So the Nielsen-Ninomiya theorem tells you that if you have an action that is quadratic in psi from psi bar, then the following properties cannot hold simultaneously. This is a lattice action, of course. Huh? So D is local, which means that D is a sort of polynomial function of the derivatives. That D has got the correct continuum limit. That D is invertible. And that the action is chirally symmetric. Okay, so these four properties cannot hold simultaneously. So which one did we break when we did a naive discretization? Yeah. Okay. By exclusion, if nothing else, right? First of all, because it's definitely local. It has the correct continuum limit. It is chirally symmetric, so it must be the invertibility. And it's invertibility because you've got 16 states. You've got 16 poles. Okay, so okay, very good. So is that catastrophic failure? No. Okay, in the sense that there are many ways out of this problem. Okay. Clearly, you want to be able to have less than 16 fermions, right? So you want to solve this problem. You want to solve the doubling problem. In order to solve the doubling problem, you will have to give up some of these properties. Okay. So with naive fermions, we gave up the invertibility. That's not a good idea. It gives us too many particles. So in order to solve this problem, we have to give up something else. Okay? Locality is not a good idea because the moment you give up locality, your theory becomes extremely complicated. So a lot of the discussions about renormalizability and so on would become extremely complicated. So we're not going to touch locality. Not going to touch this either, okay? It's nice to have the right sort of continuum limit. So basically, the solution is that we're going to break chirality, okay? So in order to solve the doubling problem, we will have to break chirality. There are many ways of doing that. We are going to discuss two of them. We will run out of time, but okay, it's fine. So the first one goes back to Wilson. It's as old as lattice field theory, basically. Okay? So this problem was realized in the very early days, and Wilson himself came up with a possible solution. And the solution by Wilson is basically inspired by Wilsonian renormalization group ideas, right? So it's very much in the spirit of what we were discussing yesterday. So the idea is that you can add to your action irrelevant operators, okay? Exactly in the sense of yesterday. So you can add an irrelevant operator, so you can add a higher dimensional operator. We're going to add a dimension 5 operator. This is not going to change the low energy physics, okay? But it's going to break chirality and solve the doubling problem. So on one hand, we will gain something because we will get rid of the doublers. On the other hand, we will lose something because we will give up chirality. Okay? And chirality will have to be recovered by sort of fine-tuning, but we will come to that later. So let's modify the action. We're going to add a dimension 5 operator, which I'm going to write in this form. There is a coefficient r in front of it, which we're going to set equal to 1 very soon. And then we have a sum over x of sum over x. What am I going to write? What do you expect? No, you have to, remember, it's a higher dimensional operator. So really in the spirit of effective field theory, somebody was saying, can we guess the order A square? Can we guess what are the operators? Yes, you can. So what's a dimension 5 operator that you can write? Psi, psi bar, derivatives, invariant under the hypercubic group. That's dimension 3. Yeah, exactly. Yeah. Derivatives. You pile up derivatives. Okay? If you do effective field theory, that's what you would do instantly. You just put dimension 5 operator, put another derivative. This is 3 halves, dimension 3, 2 derivatives, dimension 5. Here the indices are summed over, contracted and summed over. So this is even Lorentz invariant, not only not only H4 when you go to the continuum limit. What was I going to say? Yeah. And yes, there is no Dirac structure, there are no gamma matrices inside. Okay, so this has, from the point of view of chiral symmetry, this looks like a momentum-dependent mass term. Okay, so this is a psi r, psi l, psi l, psi r. So this breaks chiral symmetry. So we have given up on property number 4, and let's see what we get. Okay, so again, we don't want to go through all these sines and cosines again, so I'll try to be sort of brief. So this is the Laplacian, by the way. This is the discretized Laplacian. Okay, it's a forward derivative and a backward derivative. So delta mu star delta mu of psi of x is 1 over a squared, and then you get psi of x plus a mu plus psi of x minus a mu minus 2 times psi of x. Okay. And so when we plug this into when we write this in momentum space, it looks like, so the integral over p e to the I p dot x, and then 1 over a squared e to the I ap mu plus e to the minus I ap mu minus 2 times psi of p. Like this. Okay? So basically, we are adding to the kinetic term in momentum space a term which looks like that. Okay? So this really looks like in momentum space, as I said a moment ago, this is nothing but a p-dependent mass term. Okay? So we're adding to the kernel of the quadratic form this here. Yeah.
Is that square or sum of
Sorry, where? Which one? Here. Down. No, here, this is for every mu. Okay? And then, yes, when you put it, sorry, I never write the sum over mu. So here there is a sum over mu. Here, no, but you can add a sum over mu. Sorry, yeah. Sums over mu, yeah. Okay, yeah. So this is summed over mu. This is true for every mu. You can also sum it over mu if you like. Okay? And that's the same as that. Yeah, sorry with the sums over mu. At some stage, I lose patience. Okay, so we're adding a term like that to the kernel of the free theory. Okay, so basically we're adding this to the propagator, to the mass in the propagator, and you see the important property. Okay, well, I don't want to go through lines of algebra, but you see the important property is that this is going to break the symmetry between all the minima that we discussed for the naive discretization. Okay, because here you see that this is 0 if all p mu's are equal to 0. Okay, and instead it's something of order 1 over a if any one of the p mu's is not 0. Okay? So if all the p mu's are 0, this is just a sum of zeros. You get nothing. If you are around any of the other minima that we discussed for the naive discretization, then this is a contribution of order 1 over a. Okay. And that's basically the solution to the doubling problem. Okay, so you can propagate this change through all the steps that we have discussed before. Okay, so let me see. We can start from the equation that gave us the poles in the denominator of the propagator. Okay, we end up with P4 tilde squared plus the sum over k of pk tilde squared, and then instead of m, we get something that looks like this. You get 1 over a, the sum over k, where k only goes from 1 to 3 of 1 minus cosine apk. And then, so here I'm separating the spatial components from the time component. Here we get minus cos AP4. Okay, so this is your mass, this is your momentum dependent mass term squared. This is equal to 0. Okay, so you see without the Wilson term, this is called the Wilson term. Without the Wilson term, we only had m squared. Now that we add the Wilson term, we have this extra contribution. Okay, and so now we have to find the poles in P4, but there is a P4 dependence in here, and there's a P4 dependence in there. Okay. Again, sit down when you have a spare afternoon, you do the algebra, but you already see, right, that this is going to break the symmetry P4, so AP4 going into AP4 plus pi. Okay. You remember a moment ago the two solutions that were inside the circle, they corresponded to one value of P4, of AP4, and then the same value of AP4 plus pi. Okay? This symmetry is broken now because this term is no longer symmetric when you do that change. And so one of the two solutions, one of the two poles is gone. Okay? Do the algebra. If you shouldn't trust me, you should do the algebra, but that's the answer that you will get. Okay? So we've got rid of the second pole, and let's discuss very briefly what happens to all these minima of the energy function. Okay? Remember, for every pole we had 8 different minima of the energy function. Well, they're still there. Okay? There are still 8 minima. But they are local minima. Okay? So before, the 8 minima were degenerate. Before the 8 minima, they all gave you the same energy. Okay? Now this is no longer the case. Okay? And the value of omega at the minima, so let's write this as omega alpha. So this is the value of omega at P alpha multiplied by A, so that we have a dimensionless quantity. Now is the log of AM plus 1 plus the sum over K of NK alpha. And again, these are only spatial indices. Okay? So at the minima, we have one solution where all the NKs are 0. Okay? Where A omega is just the log of 1 plus AM. Okay? So we have one solution where A omega alpha, in the limit where AM is small, goes to M. Okay? So we have one solution where the energy at rest is equal to M. And then for all the other solutions, you see, so as soon as one of these NK is no longer 0, then this is what it is, right? It's no longer a small deviation from 1. Even if AM goes to 0, this is a number, it's a finite number, okay? And so for all other solutions, A omega at the minimum is of order 1, which means that if we send A to 0, or again, if A becomes small compared to the length scales in the game, this energy, the energy that corresponds to the other 7 minima, goes like 1 over A. Okay? So basically the mass of the doublers is lifted at the cutoff scale. Okay? And so again, if you think of the continuum limit in terms of an effective field theory, adding Wilson fermions has the effect that you keep one light state, okay? And all the other doublers are at the scale of the cutoff. So basically they will play no role in the sort of low energy dynamics of the theory. Okay? The price that we have paid is that we have broken chiral symmetry. Does that make sense? I skipped a lot of sines and cosines along the way, but it's fine. It's only sines and cosines. Okay? So you can try to do it, as I said, if you have a spare sort of afternoon at some stage and convince yourselves that this is correct. Right. Moving on slowly, we are going to discuss another way of constructing a fermionic action on the lattice. And again, we will see that we cannot escape the Nielsen-Ninomiya theorem, but we will get something which is actually very, very nice. Okay? So I'm going to discuss a different type of fermions. Whoa, they go under the name of Ginsburg-Wilson fermions. This is something that Ginsburg and Wilson did back in time. And it's a very interesting story because this paper came out in 1982 and was basically ignored for 20 years. If you look at the paper now, it has a massive number of citations. And I'll tell you why at the end. Okay? So this was a completely forgotten paper that was rediscovered at some stage and had a huge impact actually on our understanding of chirality for lattice field theories. So Ginsburg-Wilson, they decided to try to look at to try to build a fermionic action in a different way. Okay, so instead of being sort of naive and just discretized, they decided to do the following. They decided to sort of build the lattice action by integrating out from the continuum, by blocking, if you like, a continuum theory. What do I mean? Okay, so let's try to understand what that means. So remember, on the lattice, the only positions that are available are integer multiple of the lattice spacing. I'm going to call them x, and then I will introduce a continuum variable z mu. Okay, this is just my usual sort of coordinate in continuum space-time. And then I'm going to assume that I have a fermionic theory in the continuum. So my fields psi and psi bar are just the usual sort of fermions in the continuum. And now I'm going to define a lattice field. I'm going to call this psi lat, which is defined on the lattice, so only at the lattice sides. And it's going to be defined in the following way. It's going to be defined by smearing the continuum field. Okay? So, sorry, Z. So I've got my lattice. I want to define a lattice field here. I'm going to call it psi lat. And I'm going to define this psi lat as the average of the continuum field over some range. Okay? This f is a function that decays sufficiently quickly as the distance is increased. Okay? F of x decays with x. And I don't need to specify the rate at which it's going to decrease. I'm going to assume that everything that we do is fine. Okay? Let's say that it vanishes rapidly enough that we never run into trouble. So I have a continuum theory. I've defined a lattice field, and now I'm going to define my lattice action in the following way. I'll write it down again, and then we can have a brief discussion. So I'm going to define my action, and I'm going to call it a Ginsburg-Wilson action. This is going to be a function of chi and chi bar. So chi and chi bar are fields that are defined on the lattice. Okay? And this is going to be defined in the following way. I'm going to integrate out the continuum fields with a weight that looks like that. So I'm going to introduce a parameter that I'm going to call alpha, and then the sum over x of chi bar minus psi lat bar, and these are all functions of x, of course, times chi of x minus psi lat of x. Okay? So you see, if alpha goes to infinity, okay, then you get a contribution to this integral only when chi is exactly equal to psi lat, okay? Because you can do a saddle point expansion. I mean, the only when alpha goes to infinity, the only configurations that contribute are the ones where chi and psi lat are exactly the same. If alpha is not equal to infinity, you get a sort of fuzzy version of that. Okay? So the chi's are not exactly equal to the psi lat. They are sort of oscillating around this psi lat. Yeah? So this defines my action. S here is the continuum action. Okay? And let's stick to massless fermions. So this is really slash n. Okay? Or let me write it just like that in the continuum. So D is chiral. The only thing that we need to remember is that this action is the continuum action, and therefore is chirally symmetric. Okay? And now you see this object here is quadratic in psi, and in psi and psi bar. These psi lat are linear in psi. Okay? So again, this is a quadratic form which has a psi bar and a psi. Okay? So at the end of the day, this is just the integral. It's a Gaussian integral in psi and psi bar. Okay? And as usual, with a shift, which is given by chi and chi bar. So you know that when you do this integration, you're going to get something which is quadratic in chi and chi bar. Okay? What you get is not obvious at all, but you know that it's going to be quadratic in chi and chi bar. So you know that SGV of chi and chi bar is something that looks like this. the GV of x and y chi of y. Okay? And so now we want to study the chiral properties of this operator here, D. So let's do a chiral transformation, and let's see what we get. Okay. So we're going to take this expression here, which defines SGW, and we're going to perform a chiral transformation. So the chiral transformation we can write like that. So chi goes into e to the I epsilon a gamma 5. Do I need this? Do I need the lambdas? Well, let's assume that there is flavor into the game, so that this is a flavor. This is a matrix in flavor space, and chi bar goes into chi bar into the I epsilon gamma 5 lambda A. Okay, so you recognize the chiral transformation, yes? Yes or no? Yeah. Okay, good. And so now we can perform this transformation and plug in this equation here. So on the left-hand side, remember that we have a quadratic form. Okay. So on the left-hand side, we have the exponential of minus the sum over x and y, and then we have chi bar e to the I epsilon A gamma 5 lambda A dGW x and y e to the I epsilon A gamma 5 lambda A chi. So this is computed at x, this is computed at y. Okay? These are all global transformations. So this is my left-hand side. On the right-hand side, okay, we have, so this is chi independent. We've got chi bar here, and we've got chi there. Okay? So these are the two terms that are going to transform. And then remember that psi lat, so this quantity here, is linear in psi. Okay? So I can make a change of variables in the integral. I can make a change of variables which is given exactly by this chiral transformation. Okay. Remember, in this equation here, these are just integration variables. I can change the integration variables as I wish. So this is a continuous theory. The measure is invariant under this change of variables. So I get the integral over d psi bar. What happens to this term? Yeah, it's invariant, okay, because this is where I'm going to use the fact that this is the theory in the continuum. It's chiral invariant, okay? So when I change variables, this doesn't change, so I can write it again exactly the same. And now, because of this change of variables, and because these guys are linear in psi and psi bar, then psi lat and psi bar lat transform exactly like chi and chi bar respectively. Okay? So I get an overall term which looks like this. So I get an exponential, I write it downstairs, minus alpha, and then we have the sum over x, and then we get chi bar of x minus psi lat bar of x e to the 2I epsilon a gamma 5 lambda a, and then chi of x minus psi lat of x, like this. Okay? So we get a factor of e to the I epsilon a gamma 5 lambda a from this, and we get the same factor from that, so we can combine them, and we get an e to the 2I epsilon alpha gamma 5. Okay? So, as usual in these games, okay, we are going to expand everything at first order in epsilon, okay, and then on the left-hand side, if you expand this term at first order in epsilon, you expand this term at first order in epsilon, you collect everything again at first order in epsilon, and you get a minus times the sum over x and y, chi bar of x, and then you get the anti-commutator gamma 5 GW, times lambda a times chi of y, which multiplies e to the minus SGW of chi and chi bar. Okay? This is from expanding the left-hand side. On the right-hand side, we still have an integral, okay? And the integral looks like that. An integral over d psi bar, and then from expanding this term here, we get down from the exponential a factor which is minus alpha times the sum over x, and then we get chi bar of x minus psi bar lat of x. We get a 2 gamma 5 lambda a. We get chi of x minus psi lat of x, like this, times we still have the exponential times the exponential of minus alpha times the sum over x, blah, 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 minus s of psi bar of psi and psi bar, like that. Okay? This is a minus, and this dot, dot, dot is exactly the expression that we have up there in the definition of the Ginsburg-Wilson action, right? Is the leading term of this expansion. We get a chi bar psi lat, chi psi lat. Okay? So now you can compute this integral exactly, okay, simply by noticing that it's the integral that you have up, that it's the derivative with respect to chi and chi bar of the integral that you have up there. Okay? So you can, if you take derivatives with respect to chi and chi bar in the integral above, you will pull down in the integrand exactly factors like that. Okay? So you can do the integral, and the answer of this integral is minus 2 over alpha times the sum over x and y of chi bar of x, and then we get the sum over z of d GW x z gamma 5 lambda a d GW of z and y, like that, times chi of y times e to the minus s gb of chi and chi bar. Okay? So that's the result of this integral. Okay? And so now if you compare the left-hand side to the right-hand side, you see that this factor of e to the minus s GW simplifies. Okay? And we get a relation for the about that tells us something about the anticommutator of gamma 5 with this Ginsburg-Wilson operator. Okay? So we can we're going to set alpha equal to 2 over a. Remember that alpha in my original definition is just anything I like. Okay? Note that alpha goes to infinity as a goes to 0. Okay, so with this choice, as you go to the continuum limit, you're really forcing chi and chi bar to be equal to this psi lat. And then you plug that into here, the factor of 2 cancels. You get a factor over a, which you need for dimensional reasons. You take the trace over flavor to get rid of this lambda. Here the flavor is not important. It's just a technical trick. And so what you get is that gamma 5 d Ginsburg-Wilson is equal to a times d Ginsburg-Wilson gamma 5 d Ginsburg-Wilson. Okay, so this is known as the Ginsburg-Wilson relation. Okay, you see, it's so this is basically you can think of that as the sort of. So first of all, what have we got? Well, we've got that chiral symmetry is broken. We knew that. Okay, this is Nielsen Ninomiya. There's no way we can escape. We were going to break chiral symmetry, and indeed we broke chiral symmetry. The interesting thing here is that the breaking of chiral symmetry is given by an irrelevant operator. Okay, so this is an operator of dimension 2 multiplied by 1 power of a. Okay? So you can think of this as the sort of minimal amount of symmetry breaking that you obtain if you start in the continuum with a theory which is chirally symmetric. You do a blocking transformation. You use this blocking transformation. So you use this averaging, in between lattice sides to define your lattice fields, okay? And then you use this averaged these smeared fields to build a lattice action, then this is somehow the minimal amount of symmetry breaking that you're going to get. Okay? So this is called the Ginsburg-Wilson relation. Ginsburg-Wilson relation. And I told you at the beginning that this paper had been forgotten for a long time, right? And the reason the paper had been forgotten is that nobody knew how to solve this. So nobody had an explicit expression that would satisfy this equation. Okay, remember I told you a moment ago that we know that SGW is going to be quadratic, okay? But we don't know what it looks like. And indeed, nobody knew how to find an operator that had this that satisfied these properties until a solution was found. Okay, and that was a complete revolution. Actually, two solutions were found in independent ways. Both ways are extremely sort of interesting. It was two completely ways of looking at chirality. People didn't have in mind the Ginsburg-Wilson relation. They were just looking at chirality. They found two completely different solutions. It turns out that the two solutions are equivalent. I'm just going to mention one of them. This is the overlap. It's called the overlap operator. It's introduced by Neuberger. Sometimes, I can't remember. I have to apologize to Neuberger, I can't remember the exact date. Late 90s, okay? And once you have the solution, like in all problems, it's obvious that it is a solution. The difficult part is to find it, of course, right? So the overlap operator is 1 plus gamma 5 times epsilon. Epsilon is the sign function of HM, and HM is the Hermitian-Wilson, Dirac-Wilson operator. So it's W plus M. Okay? So this dW is exactly the Wilson operator that we were discussing a moment ago. H is dW plus M multiplied by gamma 5, and you plug this into the sign function. Okay. So, as an exercise, you can check that this expression here satisfies the Ginsburg-Wilson relation. It takes two lines. It's often like that once you know the solution. Okay. Epsilon is the sign function, right? 1 when it's positive, minus 1 when it's negative. So you can go to a basis where it's diagonal, and then for the positive eigenvalues, so in the directions where you have a positive eigenvalue, epsilon is the identity. In the directions where you have a negative eigenvalue, epsilon is minus 1. Final comment, and I've done half of what I wanted to do today. There is a really beautiful property which follows from the Ginsburg-Wilson relation, and if you have a Dirac operator that satisfies the Ginsburg-Wilson relation, then the lattice action is symmetric at finite A. Okay, so in the regularized theory, you have a symmetry of the action. Okay, so the action is symmetric under the following transformation, and again, you can do that as an exercise. Okay, so I write this in the infinitesimal form. Okay, 1 plus A over 2 d GW psi, and the same for psi bar. Okay, so psi bar 1 plus epsilon gamma phi 1 plus a half over 2 dgw epsilon gamma 5, yeah, like this. So if you perform this transformation here, you can show that the action, the Ginsburg-Wilson action, is symmetric. Okay? So you look at the change in the action, you use the Ginsburg-Wilson relation, and because now D appears in the transformation, you find that the action is symmetric. Now you see, this is very nice for several reasons, right? So first of all, this is not a chiral transformation, but almost, okay? So you see that if A is exactly equal to 0, this is the usual chiral transformation, okay? Epsilon gamma 5 times psi. Okay? So again, it's a modified symmetry, and the modification is of order A. Okay? So in a sense, it's a very natural generalization of chiral symmetry to the case of a discretized theory, but it's extremely powerful because this is an exact symmetry. So once you have an exact symmetry, it allows you to write word identities. Maybe we'll mention this on Friday a little bit. And so all the usual relations that you have in a continuum theory as a result of chiral symmetry can be translated into the discretized theory. Okay? So basically, all the inconvenience of having broken chiral symmetry go away because you've broken chiral symmetry, but you replaced it for Ginsburg-Wilson fermions, you replaced it with something which basically allows you to do pretty much everything. Okay? So, as an exercise, instead of doing all the sines and cosines, try that this really gives you a symmetric action and that this satisfies Ginsburg-Wilson. Okay? And we'll stop here, and tomorrow we'll add gauge fields. Okay.